Plot the bode diagram for the following transfer function and determine the phase crossover frequency, gain crossover frequency, phase margin, gain margin. Okay, given g of s is equal to 2 by s plus 1 s into 1 plus 0.4 s into 1 plus 0.1 s. So, if g of s is not given in this format, that is, if the numerator is not in this format, that is k by s into 1 plus st1 into 1 plus st2. Okay, this is the general form for the question. If it is not in the 1 plus st1 form, you should first make it in this form, then only solve the problem. Okay, it should be 1 plus st1 form. Okay, that is the general form. Okay, so let's see what are the step by step procedure to plot the bode diagram and find the gain margin and phase margin. So step 1 is given g of s is equal to 2 by s into 1 plus 0.4 s into 1 plus 0.1 s. Okay, put s is equal to j omega. Okay, so g of j omega is equal to 2 by j omega into 1 plus 0.4 j omega into 1 plus 0.1 j omega. Okay, then step 2 is the magnitude plot. Okay, magnitude plot, it has some subdivisions. Okay, so in the magnitude plot, first step is find the corner frequencies. So how can we find the corner frequency? Here you should take the general, from the general equation you should take these two terms, that is 1 plus st1 and 1 plus st2. Okay, consider these two terms and find the corner frequency where omega c1 is equal to 1 by t1 from this equation. Here it is 1 by 0.4. Okay, here it is 1 by 0.4, which is equal to 2.5 radians per second, and omega c2 is equal to 1 by t2, which is equal to 1 by 0.1 is equal to 10 radians per second. Okay, so this is the first step, find the corner frequencies, and then we are going to tabulate the column with corner frequencies in its. The terms of the column will be in the increasing order of the corner frequency. It should be in the increasing order of the corner frequency. So step 2 is the tabulation for magnitude plot. For the magnitude plot, it consists of term, and the term should be written in the increasing order of corner frequency. Term should be written in the increasing order of corner frequency. Then the next column is corner frequency in radians per second. Then we have slope in dB per decade. Then we have change in slope. Okay. So these are the terms. In the tabular column, which is dB per decade. Okay. So our first term is 2 by j omega. Always select the constant term along with integral term or derivative term. If it is 2j omega, then take the first term as 2j omega. If it is a constant k, that is if it is only 2 by 1 plus st1 into 1 plus st2, then take 2 alone or k alone. Then the for constant the slope is 0 dB per decade. Okay, and it doesn't have any corner frequency and it has a slope of minus 20 dB per decade and there is no change in slope. Okay, so next step, I can take both 1 plus 0.1 s and 1 plus 0.4 s, but I should take in the increasing order of the corner frequency. So increasing order of the corner frequency, we have two corner frequency 2.5 and 10. So I should take the one with corner frequency 2.5 first, then I should take the corner frequency 10. So I should write in the increasing order of the corner frequency. So first term is 1 by 1 plus 0.4 j omega. So that is my second term and my corner frequency is omega c1 is equal to 1 by 0.4, which is equal to 2.5, and my slope is minus 20 and my change in slope is minus 20 minus 20. Okay, which is equal to minus 40. Okay, so I should add. If it is plus 20, then it will become 0. Since it is minus 20, it is minus 40 dB per decade as the change in slope. So the next term is 1 by 1 plus 0.1 j omega. Okay, 1 by 1 plus 0.1 j omega. Now omega c2 is equal to 1 by 0.1, which is equal to 10, and the slope is again minus 20, that is minus 40 minus 20, which is equal to minus 60. Okay, so the tabulation for the magnitude plot is over. Okay, now next step is step 3 under the magnitude plot. Okay, next step is choose a lower frequency omega L and a higher frequency omega h such that omega L should be less than omega C1 and omega H should be greater than omega C2. Okay. So, this is the next step. Omega L should be less than omega C1 and omega H should be greater than omega C2. So, we should choose it by our own. So, I am choosing let omega L is equal to 0.1 radians per second, okay, and omega H is equal to 50 radians per second. Okay. So, this is the step 3. Now, step 4 is find the magnitude of G of j omega, where A is equal to mod G of j omega. Okay. So, magnitude is denoted by A, which is equal to mod G of j omega. So, how can we find the magnitude? So, for that, take at omega is equal to omega L. Okay, omega L is taken as 0.1 radian per second. A is given by 20 log first term. Okay, mode of first term. So, here first term is 20 by j omega. Okay, always take A is equal to 20 log first term. So, here in the table first term is 2 by j omega. Okay, according to our table, if there is only constant, then 20 log constant. If it is 20 log k j omega, then take it as first term is k j omega, take it as 20 log k j omega. So, always take the first term as 20 log mod of 20 by j omega. First term is 20 by j omega. So, it is equal to 20 log 20 by omega. Okay. Then give omega is equal to omega L, that is equal to 20 log 20 by 0.1. Okay, so since omega L is equal to 0.1, I put 0.1 and I will get 26.02 dB, which is approximately equal to 26 dB. Okay, so at omega is equal to omega L, equation for A is 20 log the first term in the tabular column. Now, at omega is equal to omega C1 also, A is equal to 20 log first term. Okay, always take this equation for omega is equal to omega L and omega is equal to omega C1. That is, for the first two terms we are taking 20 log the first term. Okay, so here omega should be given omega C1 value 20 log mod 20 by omega C1 is 2.5, okay, which is equal to minus 1.94 dB, which is approximated as 2 dB, minus 2 dB. Okay. Now, at omega is equal to omega C2, I have a different equation. A is equal to slope from omega C2 to, so first omega C1 to omega C2 into log omega C2 by omega C1 plus A at omega is equal to omega C1. Okay. So, for omega is equal to omega C2, the equation is A is equal to slope from omega C1 to omega C2, that is the change in slope from omega C1 to omega C2 into log omega C2 by omega C1 plus A at omega is equal to omega C1, that is, okay. So, here my first change in slope is minus 40. So, from omega C1 to omega C2 I should take the slope as minus 40. So, minus 40 log omega C2 is 10 and omega C1 is 2.5 plus minus 2 dB. Okay. So, I will get minus 26.08 dB, which is approximately equal to minus 26 dB. Okay. Now, at omega is equal to omega h, A is equal to slope from omega C2 to omega h into log omega h by omega C2 plus A at omega is equal to omega C2. Okay, that is, here the slope is minus 60 dB. Okay, so minus 60 into log omega h is taken as 50 divided by omega C2 is 10. Okay, plus minus 26, which is equal to minus 67.93 dB approximated as minus 68 dB. Okay. So, I have got all the values of magnitude at omega L, omega C1, omega C2, omega H. Okay. Now, step 5 is plot the magnitude. Okay. In semi-log paper. Okay. Plot the magnitude vs frequency in semi-log paper. So, magnitude plot is over. Now, step 3 is the phase plot. Okay. So, step 3 is the phase plot. Okay. For that, we should find the phase angle. Okay. We should find the phase angle. Phase angle phi is equal to angle of G of j omega. Okay. And we have G of j omega as 20 by j omega into 1 plus 0.4 j omega into 1 plus 0.1 j omega. Okay, this is our question. Okay, so I have already explained how to find the angle of this each of the term. Okay, so I have first term 20 by j omega, so minus 90 degree. Okay, minus 90 degree minus tan inverse. Okay, I have 0.4 omega by 1. Okay, so 0.4 omega and minus tan inverse 0.1 omega. Okay, so for this I have minus 90. If it is j omega square, then it will be minus 180. Okay, now for this I have tan inverse b by a. Tan inverse minus, since it is in the denominator, it will come minus tan inverse 0.4 omega divided by 1, that is 0.4 omega, and for this term it is tan inverse 0.1 omega by 1. Okay, so tan inverse 0.1 omega. Now we have to make the tabular column with omega in degrees and phi in omega in radians per second. Okay, omega in radians per second and phi in degrees. Okay, I have to make the tabular column. Okay, so here the first one is omega L 0.1. Okay, now second one should be 1. I'm just taking some values. Now I have omega C1 2.5 and omega C2 it is 10. Okay, before 10 I am taking 5. Now omega C2 10 and omega H I have taken it as 50. So 50. So I have taken like this values. Now how to get the values? So first just write the equation here. 90, I have taken math and in degrees, so minus 90 minus tan inverse for 4 shift a. Okay, so I am taking in the omega place, I am giving it as an alphabet 0.4a minus shift tan inverse 0.1 a. Okay, this is my equation, minus 90 minus tan inverse 0.4 omega minus tan inverse 0.1 omega. Okay, so then just press the calculation, just press and give the values. If it is 0.1, give the value and you will get minus 92.86. Okay, so I am approximating it as minus 92. Okay, minus 92. Next, again press calculation, then and give 1. I will get minus 117.51. So I am taking it as minus 118. Okay, again calculation 2.5. I will get minus 149 point, and I am taking it as minus 150. Okay, again calculation 5, I am getting it as minus 180, minus 180. 10, I will get minus 210, and for 50 I will get minus 236. Okay, so every time you don't want to write the equation, just write it once and calculate for each value. In the same way how I have shown. Okay. So now in order to next part is plot the phase with respect to omega. So now let's move on to the plotting part. So I have a semi-log paper here and it should be kept like this, okay, with semi-log paper cycles into 1 into 10 raised to n, okay. So it should be kept here and its divisions are given as 1 to 9, 1 to 9, 1 to 9 and 1 to 9. Okay, so here we are going to write omega, that is frequency in the x-axis, as fixed, and here I am plotting the gain and here I am marking the phase angle. Let's do it together. Okay. So I have this one here and okay, so first we have to write the x-axis omega in radians per second, okay, and here I have gain in dB. Okay, so how the marking should be? So here it is taken as 10 raised to maximum value, it can take as 10 raised to minus 1, that is 0.1. Okay, usually 0.1, 10 raised to minus 1. Okay, 10 raised to minus 1. So this 2 will be 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9 and we have 1. Okay, so that is 1. That is 10 raised to 0. 10 raised to 0. Now it is 10 raised to 0. 1, 2, 3, 4, 5, 6, 7, 8, 9 and here we have 10. That is 10. That is 10 raised to 1. Okay, 10 raised to 1. Now here I am having 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, so I will write 100, that is 10 raised to 2. Now this will be 1000, 10 raised to 3 and this will be 10 raised to 4. Okay, so it will be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 200, 300, 400, 500, 600, 700, 800. Okay, so that is how the values varies, okay, in the x-axis. This should be always remembered. Okay, now I am going to plot the magnitude and I have the table here. For plotting the magnitude, I have the table here and I have the values here. Okay, so if we look at the values, its first value starts at 26 dB and the last value ends at minus 68 dB. Okay, so I can take this as my 30 dB. Okay, 30, 20, 10 and 0 dB, minus 10, minus 20, minus 30, minus 40, minus 50, minus 60 and minus 70, because last value is minus 68. So I have taken towards the top 30 because it's plus 26 and minus 68. Okay. Similarly, you can take the values, and so for 0.1 omega L, when omega is equal to omega L, you have 26 dB. When omega is equal to omega C1, okay, this is 0.1, this is 2.5 and this is 10. Okay, so it is minus 26, minus 2 and plus 26, minus 2 and minus 26. So I am marking it here. So it is 20 and 30. So 22, 24, 26. Okay. So my point is this one. For omega is equal to 0.1, I have this value. Now for omega is equal to 2.5. Okay, here I have 2 and in between I have 2.5. I have the value minus 2 dB. So this is 0 and this is minus 2 dB. So my value will be here, the 2.5. Okay, here I will mark the here I will mark the 2.5. Okay, then I have minus 26 dB for omega is equal to 10. Omega is equal to 10, I have minus 26 dB. So I have marked here minus 26, and for omega is equal to omega h, that is for 50. Okay, this is my 50. I have minus 68 dB. Okay, so I have marked all the points. Now draw it with scale. So magnitude plot are always drawn with the help of scale, while phase plot are drawn with in the free hand. Okay. Okay, so I have drawn it with pencil. Now this is minus 20 dB per decade, this is minus 40 dB per decade, and this is minus 60 dB per decade. Okay, so this is the magnitude plot. Now we have to draw the phase plot, and I am taking a point here. Okay, phase in degrees, and my last value for the phase plot is minus 236. So I am taking the last value as minus 240. Okay, so first minus 240, then I am taking minus 220. Okay, I am going to use the pen. Minus 220, minus 200, minus 180 minus 160 minus 140 minus 120 minus 100, and I have minus 80. Okay, this much values are enough for our purpose, and we are going to plot the same way from here. Okay, so omega is equal to, I have omega is equal to 0.1, 1, 2.5, 5, 10 and 50. So here it is 20 degree, that is I can take my 1 degree as 4, minus 84, minus 88, minus 92. So the third line is minus 92, minus 96 and minus 100. Okay, so 1 division is 4. So I can mark it here, that is for 0.1 it is minus 92. Okay, so for 0.1 radians, I have minus 92. So I have marked all the points. Now I am drawing it in the freehand. Okay, so joining it free-handedly. Okay, so I have drawn it free-handedly, the phase plot, and I have the 180 degree here. So 180 degree is here, and here I have the 0 dB line. Okay, so now I have to find the phase crossover frequency and the gain crossover frequency. So phase crossover frequency is the phase is corresponding at which frequency the phase is crossing 180 degree. So here 180 degree is crossing at 5. Okay, so 5 is the phase crossover frequency, WPC. Okay, so phase crossover frequency is the frequency at which the phase crosses 180 degree. Okay, that is 5, and the gain crossover frequency is the frequency at which the gain crosses 0 dB. So here it is a 0 dB line, and the gain crosses at 2. So omega GC is equal to 2. Okay, at 2 the gain crossover frequency is omega GC is equal to 2. It crosses the 0 dB at omega GC is equal to 2. Okay, so I got gain crossover frequency omega GC. Gain crossover frequency is the frequency at which the magnitude plot crosses the 0 dB, and that is at 2 radians per second, and omega PC phase crossover frequency is at 5 radians per second. Okay, so omega GC and omega PC, I have got omega GC and omega PC. Now I have to find the gain margin. So for that, extend the omega PC towards the magnitude plot. Extend the omega PC towards the magnitude plot, and it will give the magnitude as minus 14. Okay, so it will corresponding to the phase crossover frequency. I have the phase crossover frequency here. I extended it towards the magnitude plot and I got it as minus 14 dB. So my gain margin is negative of minus 14, which is equal to 14 dB. Okay, so negative of minus 14, that is 14 dB is my gain margin, and my phase margin will be this one. Okay, what is it? Corresponding to the here, corresponding to the corresponding to 0 dB. Okay, this one, this value from 180 dB to this omega GC 0 dB line. Okay, from minus 180 to 0 dB line, what is this difference? Okay, here I have got minus 142. Okay, minus 142 as 5 GC, and my gain margin, phase margin is gamma is equal to minus 180 or 180 plus 5 GC, which is equal to 180 minus 142, which is equal to 38 degree. Okay, so this is my phase margin, or you can measure this. We have 20 and we have 142. Okay, that is corresponding to 142 degree. I have the gain margin, so we will be having 38 degree as the phase margin. Okay, so this is how we are getting the phase margin and gain margin. Find the gain crossover frequency, find the phase crossover frequency from the graph, and find the gain margin corresponding to phase crossover frequency, and find phase margin corresponding to the gain crossover frequency. Okay, now once we have found this, then we can say about the stability of the system. That is, if both margins are positive, okay, both margins are positive, or phase margin is greater than the gain margin, then the system is stable. That is, I have the plot and the gain crosses 0 dB at omega GC, gain crossover frequency. Plot it towards the phase and I will get a point. So this distance will be my phase margin, and the phase crosses minus 180 at this point. Plot it towards, extend it towards the magnitude plot, then you will get this as the gain margin. Okay, this both are positive. Okay, so we said gain margin is minus of minus dB. Okay, so this is positive and this is positive. If both are positive, then the system is stable. Okay, now if both are 0 or both are equal, then the system is marginally stable, and if any of them is negative or phase margin is less than the gain margin, that is, here it is negative and here it is negative. Okay, so such a system is unstable system. If any of this happens, then the system is unstable, and if both of these happen or the phase margin is greater than the gain margin, then the system is stable. Hence we can find whether the system is stable or not using the phase margin and gain margin. Here we have both. So this is our phase margin and this is our gain margin. Okay, so this is positive and this is positive. Since both are positive, the system we considered here is a stable system. Hope you understood it. If you have any queries, please do ask me in the comment section.